Hello everybody, welcome to another video lesson. We are looking at dot products in space in this lesson. All we're going to do is find the dot product and angles between vectors in three-dimensional space now, since we have been looking at vectors in a three-dimensional space context. So let's hop right into our concepts. Okay, so for our dot products, our two-dimensional formula for our dot products is just going to be our A1 times B1 plus our A2 times B2, assuming that, let's say, vector A is going to equal A1, A2, and then vector B would be B1, B2. Okay, that's our two-dimensional situation, but now in a three-dimensional context, if we have vector A, that would be, of course, A1, A2, A3. Okay, writing this in component form, and then B, vector B would be B1, B2, and B3. Okay, again, in component form. So really all we're doing is the same process here, except now we have this third component, right? This is kind of like our Z component. So all we're doing is adding the product of our two Z components to the end of our two-dimensional formula for dot product, and there we go. We've got our dot product in 3 dimensions. Now, again, orthogonal vectors are vectors that are parallel to each other. If we take the dot product of those, and that is 0, then that means that we have orthogonal vectors, okay? So that does not change between 2 dimensions and 3 dimensions, all right? So that is the only concept that we're going to look at today. So let's go ahead and take a look at our dot products in space. Okay, let's find the dot product of U and V, vector U and vector V, and determine if they are orthogonal vectors, all right? So vector U, it's given in a linear combination of unit vectors I, J, and K, and the same with vector V. So I'm going to go ahead and rewrite these in component form. Okay, so vector U, I'm going to say we have U1, U2, U3, and vector V would be V1, V2, V3. So the dot product of the two, so U dot V is how we'd say that, remember? So it's going to be U1, V1 plus U2 times V2 plus U3, V3. So all we got to do is plug those in. So I'm going to get 15 minus 35 plus 20, and U dot V is equal to 0, which means we have orthogonal vectors. Okay, so with that same process, you guys go ahead and try to find the dot product of U and V, and then determine if they are orthogonal vectors. Okay, here's my process. U dot V is equal to 4. Which is not equal to 0, so that is not orthogonal. These vectors are not orthogonal. Alrighty, now let's take a look at the angle between two vectors. Again, we're looking at this in three-dimensional space. However, our formula does not change at all. Okay, cosine of theta is equal to A dot B all over the magnitude of A times the magnitude of B. So in this case, it's just going to be U dot V over magnitude of U times magnitude of V. So U dot V would be our I components. Now notice I don't have a J component here for vector V. Okay, there's no J, so that's why I have a 0 here for the J component of vector V, right? And then I'll have my K components multiplied together. That'd be 1 and 3. And we have the magnitude of both of these, so the square root of the square of each component of -4 squared plus 2 squared plus 1 squared. That's for our vector U. And the magnitude of vector V would be 4 squared plus 0 squared plus 3 squared. And we can go ahead and simplify that a bit. That's going to give us -13 over 5 root 21. And I can go ahead and rationalize that, although we really don't even need to do that because we're just going to plug this right into a calculator. I'm going to take the inverse cosine of both sides to find our angle theta. And when I plug that into a calculator, I get theta is equal to approximately 124.6 degrees. Okay, so using that exact same logic, that same process, go ahead and find the angle between these two vectors u and v. Pause the video, check that out. Okay, hopefully you got approximately 168.6 degrees. This would be the process to find our angle. And guys, that is it. A nice short video for us today. That is all I got for you, so good luck with your practice.